Welcome back to the channel. Today's demonstration, as indicated by the thumbnail, needs an introductory explanation so that the viewers get a clear understanding of the process. So let's try to understand the attack process here with the help of this infographic image. As you can see here, the attack process in today's demonstration is of a command and control remote access Trojan, where Windows 11 computer is used as an attacker on Android device used as target in my own test environment. Similar to earlier demonstrations, again, a pair of scripts called server.py and client.py is used here as well. But contrary to earlier demonstrations, in today's demonstration, we will plant the client.py script as an application to the target Android device, when we will retain the server.py script with the attacker Windows 11 computer. The reason why the Trojan here is called modular is that the tasks to be performed by such attack are inside the server.py script with the attacker computer, which can be altered from time to time on the attacker computer for the same client.py with given configuration on target Android device. It is important to note here that the tasks in the form of modules used here are harmless for demonstration purpose, but that can be altered to be harmful. So, it is labeled as dangerous to caution the users of the scripts and workflow here. The workflow and scripts used here are made available in the description box below. Anyways, the picture here enumerates the social engineering as Module 1, when actually the other three modules are hard-coded inside the server.py. So far as social engineering for implanting the client.py as an application to Android device is concerned, that can be performed either by embedding or by IMSI device or by any other application having embedded the application shown here. Keeping in mind that attack application will work only by physical installation and opening the application, according to Android sandbox safety features. This sandbox features will always ask the user of Android at the time of installation. Nevertheless, the other three hard-coded modules from 2 to 4 in the image works through the implant or the RAT of client.py script residing on the Android device. Since it utilizes the Toga framework, it can be compiled into a standalone Android APK. When the said application with client.py script is running on the Android in its background threading, the thread spins up a beacon function. This function continuously attempts to establish an outbound TCP connection to the Windows 11 attacker machine. This is the core mechanism of the RAT. When the client receives a script from the server, it temporarily overwrites standard output. This means anytime the dynamically executed script calls print, the text doesn't go to the Android device's screen or logs. It is routed directly over the TCP socket back to the attacker. When the Android device receives the JSON payload, it extracts the part of server.py script named as code therein and runs it locally using Python's exec function. Because the execution uses a persistent self-context, variables, and imports, which can technically be shared between modules. In the process, the server.py script acts as the C2 server, managing the remote session and directing the Android client on what to do. In doing so, the listener binds to port and waits for the Android APK. Then TCP streams fragment data, sending half a JSON object at a time. The server appends a custom delimiter. The Android client buffers incoming data until it sees this delimiter, ensuring it only executes complete, uncorrupted Python scripts. Once the Android device connects, the server automatically iterates through a list of Python scripts called modules, sending them one by one. It waits for the Android device to reply with a finish marker before deploying the next stage. The server constantly monitors the hijack print function output coming back from the Android device. If it sees the string XFIL, it knows the Android device is sending a stolen file. It extracts the base 64 data, decodes it, and saves it to the Windows machine with the prefix stolen. So far as the hard-coded modules are concerned, the server sends code to map out the Android environment. Because modern Android utilizes application sandboxing, the app cannot arbitrarily read the whole phone. The code uses OS path expand user to locate the app's specific isolated data directory. It checks if it has write permissions and sends this status back to the attacker using the hijack print command. Now knowing the writable sandbox path, the server sends code to interact with the file system. It creates a dummy SQLite database named user_creds.db inside the Android app sandbox and injects fake credentials into it. In a real-world scenario, an attacker might use this stage to modify legitimate databases belonging to the app, alter shared preferences, or download further secondary payloads. Lastly, the final module here searches the Android app sandbox for high-value targets, as in this case, any file ending in .db. It opens the database file. It packages the data into a specific format. In the end, it calls print, which pushes the packaged data through the socket back to the Windows 11 C2 server. For practically understanding the said process in motion, let's now move on to its performance as shown next, followed by demonstration of investigative steps to find out such attack on Android device. So, first open Notepad and write the client.py script as shown here. Note the IP address and port used in this script happen to be of the attacker computer. To verify, open a terminal on this attacker Windows computer and run the ipconfig command. Now, one can see for himself that the shown IPv4 address matches to that mentioned in the script. Now for the port, one first needs to add firewall rules for allowing inbound TCP connection on attacker computer for the process to be successful. So, for that, now open a Windows PowerShell terminal as administrator and run the command as shown here. Now, save this client.py script as shown here in desired location. Then create another script named server.py as shown here. Note that this initial server.py script is intentionally left incorrect as to the last two modules in it, so that the alteration capability can be shown by correcting it for rerun with the same unaltered client script already running on target Android device. Also note that this script is configured to listen to all IPs. Also save the script in desired location. Now, for making the implant application using the client script, first open Kali Linux virtual machine. Next, mount shared folder like this, so that client script can be imported to Kali Linux for converting the script to application. After mounting shared folder on Kali Linux, move the client script to shared folder on the Windows computer to make it accessible on Kali Linux. Now access the script on Kali Linux and move the script to any other location so that the script remains accessible irrespective of such mounting. Now we begin converting the client script to application that will be implanted on target Android by setting up the workspace for that. So, this command here is for installation of core system dependencies that are required. I have already run the command earlier and the dependencies are already installed. Now, this set of commands are for initializing workspace and environment variables. The last command here is for final installation of the most important tool required for making the set application. These commands here are optional, which I have run to overcome the space constraint on Kali Linux that I could be confronting otherwise during making the application. Now, these two commands here will run the wizard from inside the necessary folder so that the native Android scaffolding with metadata can be generated as shown here. Then insert the settings as shown here. See that the template for the application is already generated. Now, to modify the application according to needs, which in this case is to implement WAN-ready C2 logic, first navigate to and then open the newly created app.py script as shown here. After opening the app.py script, first remove its existing contents. Then open another terminal, navigate to and open the client script, which was imported from Windows Computer. Now copy this client.py script to the app.py script on another terminal. After copying the file contents, close the new terminal with client.py script and save the app.py script and exit as shown here. Now navigate to Open and add permissions to pipeproject.toml file as shown here. This is required to ensure that the APK will have the authority to stay active in the background on target Android. Finally, the 3 commands here will make the required APK for Android implant. To see that the APK is created, the next two commands here will locate the application and verify that the application is actually created. Now, the first command here is to copy the created APK to shared folder after having it renamed according to one's choice. This will enable the Windows computer to fetch the APK after shared folder is mounted on Kali Linux by this second command. Finally, verify that shared folder contains the said APK. Now on Windows, move the APK from its shared folder to any other location of choice so that the APK remains accessible even after the Kali Linux is shut down. Now shut down the Kali Linux, as its purpose is presently over. Now I upload the APK to Drive so that its implant on target Android can be mimicked. Now on attacker Windows computer, navigate to the server script. Now download the said APK and install it on target Android, mimicking its implant in real-world scenario. Now run the server.py script on the attacker computer, and then open the APK on target Android, as shown here. See for yourself that the attack connection is successfully established, but that the rest two modules in the server script, as to injecting database and exfiltrating the database, are failing. Now, this situation can be addressed by making necessary alterations to the server script on attacker computer for the same client script as APK on the target Android, as shown here. This signifies the indefinite nature of vulnerabilities that such modular C2-RAT attacks come with. After altering the earlier server script on attacker Windows computer, now see that the new attack on attacker's choice successfully injects the database file to target Android and steals the same database file from target Android to attacker Windows computer, all in the background. If one looks at the location of server script on attacker computer, he can see for himself that a new database file is created there, which is stolen from the target Android. Since the database injected to target Android and stolen therefrom to attacker computer are SQL database files, the stolen file can be viewed on attacker computer using DB browser as shown here. Lastly, for investigating such attack on target Android, one needs to connect the Android to a desktop over USB and needs to enable ADB, as shown here. If anybody wants to install ADB, can refer to the video in the above I button for necessary know-how. This first command here will show all applications on the connected Android, no matter pre-installed or installed afterwards. This command here will only show the third-party applications which the user has installed. After entering the command, one can identify the attacking application, as shown here. The command shown here will reveal which application is currently running on the foreground of Android. Now, this command here will reveal the UID of any application once you have identified it by the second last command here. This UID of any application associates it with its internal properties. Lastly, this command will look for any connection which will usually be shown to be on listening by the target Android for server on the attacker computer, as shown here. In this case, the highlighted address here is the gateway IP address of the attacker Windows computer. For confirmation, one can go back in this video and see the output on running ipconfig command near the beginning of this demonstration. There are other commands like these, which further helps in such investigation, but I have not covered those here to keep this demonstration as concise and compact as possible. That's it for today. Hope you have liked this video. Thanks for watching.